with his powerful brainwaves cradled in the warmth of reasoning. It's time for Johnny Walker Dread to straighten you out on a thing or two. Emanating all the way from exciting Las Vegas, Oklahoma, it's the Johnny Walker Dread Show.
Therefore, this thesis, and you may wonder, what thesis? Well, some time ago, he basically piled up a bunch of work by Shabana and Quedenberger, which basically means he copied and pasted and wrote some comments of his own and submitted it to the Asia Pacific School of Business in exchange for an advanced degree, along with some money, of course. He didn't actually do any research of his own. He basically leans on Quedenberger for everything. And so this thesis, he basically has just packaged as a book, and he was so lazy that he didn't even go back through the book and change these statements like this thesis. I mean, all he had to do was change thesis to book and he would have got it. But even that was too much trouble for him. Okay, therefore this thesis, which primarily focuses on the ancient Egyptian civilization, proposes that the cosmos and observable physical world are composed of varying vibratory frequencies. Yeah, I would love to see the hieroglyphics that make that kind of statement. The remainder of this discussion begins by outlining the guiding theoretical framework used to contextualize this thesis, the quantum field theory. Next, an overview of the ancient Egyptian culture and practices is explored in relation to this theory, with emphasis on their understanding, interaction, and application of the dynamics of the quantum field through the manipulation of vibration and sound. There is where he makes his big mistake. And it discloses the problem that his entire thesis has with trying to equate the quantum field theory as we know it and this whatever quantum field theory he's claiming the ancient Egyptians already knew. And it's really quite simple. You cannot learn quantum field theory through sound. Quantum field theory, by the very nature of the word quantum, is a subset of quantum physics, not classical physics. Unfortunately, you cannot learn quantum physics by studying classical systems, and sound is inherently classical. Let me show you what I mean. Okay, so here is an animation of sound, and this is how sound works essentially. So on the top one there, you see this kind of gray bar on the left that's kind of moving back and forth. You can think of that as like a speaker cone or maybe a drum head or a guitar string. Something is vibrating back and forth. And what does it do? Well, when it's moving to the right, it crams air close together. And then when it moves to the left, it leaves an area largely unpopulated. In other words, a very low density area. So where you see the particles crammed very close together, that represents a high pressure region. And where they are spaced far apart, that's a low pressure area. And you'll notice that as this diaphragm, or whatever you want to call it, moves back and forth, that this high-low pressure region seems to travel to the right through space. Now, you'll see that there's also a red dot there. That's to show you what an individual particle does. And you'll notice that the individual particle doesn't really move around much. It's the effect of this bunching of particles and the spacing of particles that appears to travel down the tube, okay? But you'll notice that. Now, you wonder, well, how does this create sound? Well, suppose that you have an eardrum that's located on the very far right, okay? As these high-low pressure regions travel to the right, they will alternately hit the eardrum. When a high pressure region hits the eardrum, it will force the eardrum to the right. And when a low pressure region hits the eardrum, it will suck it back to the left. So ultimately what happens is that your eardrum will vibrate back and forth at the same frequency as the drum head. This rocking back and forth is picked up as an electrical signal by your neural system sent to your brain where it is processed as sound. But here is the problem. This is an inherently classical system. In other words, there's nothing quantum mechanical about it. There is a principle in physics called the correspondence principle, but that basically says that if you take a quantum mechanical theory and you make it macroscopic, in other words, you raise its energy levels up to the point where it starts to reflect the perceivable real world, then that quantum mechanical theory will mimic classical theories exactly. However, it doesn't work in the other direction. You can't take a classical theory and by lowering the energy levels recover quantum mechanics. So in this case here, reducing the particles down or reducing their energies won't produce a quantum mechanical sound effect. It will just simply eliminate the sound altogether. So the Egyptians could have played guitars and drums and stuff all to their heart's content, but they would never have been able to perceive a quantum mechanical effect from that. So we have one problem already with Rashad Richey's claim that the Egyptians understood quantum field theory. The Egyptians did not have access to any systems that exhibited quantum mechanical effects for them to have learned quantum field theory. And as I said before in my previous video, theoretical physics is built on the foundation of experimental results. And there are very few exceptions. The conservation of energy, conservation of momentum, and the second law of thermodynamics are the only ones I know that can actually be deduced from what we call first principles. In other words, without having experimental results. All of our other theories are built on experiment, but you have to have experiments that can get down to the quantum mechanical level, and the Egyptians didn't have that. But there's another huge problem with Rashad Richey's claim, and that is the frequency here is very clear. The frequency is basically how rapidly that gray bar moves back and forth, the number of times it oscillates per second, as measured in hertz. However, this frequency has nothing to do with the frequency of quantum field theory. In fact, we don't even know what frequency is in quantum field theory. We can't envision it. The only model I know of for frequency was developed by Richard Feynman. But what is the frequency associated with quantum field theory? Well, nobody knows. The easiest to understand model that we have was developed by Richard Feynman back in the 1950s. His take on the physical world is that matter, including electromagnetic waves, is composed of photons. These are particles that travel from one place to another, rather than electromagnetic waves. And his book, Quantum Electrodynamics, is a very easy read, doesn't require any advanced mathematics. If you can square a number, you can understand where he's coming from. And so if you look at the photon as a particle, he envisioned the particle as having something like a clock hand on it. And as the particle traveled from one place to another, this clock hand would spin. So I know what you're thinking. Well, like the photon is like a spinning clock. No, it's not, because this clock hand corresponds to the probability amplitude of the photon being at a particular point in time and space. And this probability amplitude is imaginary valued. It's not real valued. So it's not a physical property. Furthermore, it spins in imaginary space. So the probability amplitude of the photon, which is itself imaginary functioned, spins in imaginary space, and the rate at which it spins, how fast it spins, is the frequency associated with that photon. You can see there is no semblance whatsoever between the frequency associated with quantum mechanics and that of sound. They are completely different things. But Rashad Richey doesn't understand that. So when he hears that the ancient Egyptians are playing musical instruments and they understood frequency associated with sound, well, that must be like the frequency that appears in quantum field theory. He's simply wrong. He doesn't get that. But any undergraduate physics major would know the distinction. And that's why I say he has no physics background at all. None. He's never passed an introductory physics course. Nevertheless, owning advanced degrees in the subject. Okay, so going back to the introduction, I'm going to skip all this. He basically borrowed this from Quenberger, And skip on down to the very final line. It says here, QFT was developed in the early 1900s by physicist Paul Dirac in his attempt to quantify the electromagnetic field. Wrong. Dirac was trying to quantize the electromagnetic field. I mean, we have quantified the electromagnetic field for almost 200 years now. It's in newtons per coulomb. Quantizing the electromagnetic field, well, that's a different story. But again, Rashad Richey made this mistake because he doesn't understand the difference between quantify and quantize. He read this, didn't realize there was a mistake. I read it and immediately caught it. Because as it stands, his sentence makes no sense whatsoever. But he's just not knowledgeable enough to catch it. So is his book worth anything? No, I can guarantee you that it's basically Querenberger and Shabana mixed in with various comments that he has that make no sense whatsoever. Like my video and subscribe to my channel.